a man who turned the world upside down with his genius, concealed a secret that could have destroyed his career and life. Isaac Newton was not just the father of modern physics. Behind the triumph of the Principia and the laws of motion lurks a heretic, alchemist, and seeker of ancient wisdom who rejected the Trinity, spent years deciphering biblical prophecies, and believed that God literally creates space through his presence. He spent more time on theology and alchemy than on physics. How did one man unite mathematics with mysticism, science with heresy, and why were his true beliefs hidden for 3 centuries? Part 1. Setting the philosophical scene. Back in 1661, Newton found himself at Cambridge University just as Europe was buzzing with intellectual debates. At the time, Cartesianism was gaining traction, challenging the established Aristotelian views and new experimental approaches. René Descartes had this notion that the world operated like a huge machine governed by mechanical laws and denied any action at a distance. He was all about the idea that matter could only influence other matter through direct contact, and he saw space as just crammed with bodies. In Descartes' view, there was no empty space, only matter spinning in big vortexes. A lot of people bought into this because it got rid of spooky forces in nature, but some weren't so sure, thinking it left little space for God, aside from kick-starting the universe. Newton stumbled onto these debates pretty early, and they left a big impression on him. He dug deep into Descartes' works, but eventually pushed against nearly all his big ideas. This wasn't just a small disagreement, but a profound conflict touching on basic metaphysics. While Descartes thought matter only filled space, Newton argued that space existed independently of matter. Newton felt that absolute space was the framework for his entire system, claiming space wasn't just about relationships between objects, contrary to Descartes' belief. Instead, space stood alone, filled or not. This was a game changer, giving space an almost godly quality. Newton even linked space with God's universal presence. In the second edition of the Principia's General Scholium, he claimed God's omnipresence essentially created space. This view shook Descartes and Leibniz supporters, who saw God as outside the physical realm. To Newton, putting God outside of space was like denying his existence. Everything, including minds and souls, needed to be tied to space. Otherwise, it didn't exist. This perspective unsettled some people who felt it made the divine too physical. Newton also didn't go for Descartes' view on motion being purely relative to nearby bodies. Descartes suggested motion was about changing positions relative to immediate neighbors, so you couldn't definitively say if something was moving or still. It all depended on your perspective. Newton believed this approach couldn't build stable laws of motion. He needed absolute motion and space for his dynamics to make sense. He used his famous spinning bucket experiment to argue that true rotation was distinct from just appearing to rotate. When water climbs the sides of a spinning bucket, Newton explained, it demonstrated real rotation relative to space. Still, Newton wrestled with a big problem he never fully solved. Absolute space and time aren't directly observable or measurable in experiments. We only see relative motions and positions among visible objects. Newton acknowledged this, saying that direct observation of absolute quantities was beyond our reach. So he proposed using absolute space as a base concept, so physics could go forward. He suggested using measurements derived from theory to infer properties beyond direct observation. Real forces acting on a body separated true from apparent accelerations, ensuring real motion could only change through direct force. This created challenges leading to philosophical debates for centuries. Even though Newton claimed to derive his ideas solely from experiments and phenomena, critics argued he relied on metaphysical concepts beyond observation. This debate got famous through his spat with Gottfried Leibniz, who came up with relationalism, the opposing idea that space was simply the relationship among physical objects. Time's all about how events unfold with different things involved. Leibniz didn't buy the idea of absolute space because it went against the principle of sufficient reason. Between 1715 and 1716, a famous letter exchange took place where Samuel Clarke stood up for Newton against Leibniz's views. Their debate wasn't just about the basics. It covered physics, metaphysics, and theology, and neither was ready to give in. Both understood that their discussion delved into God's link to creation. This wasn't just high-level philosophy. It was about the deep stuff concerning divine intervention. Newton believed God was actively involved in keeping the universe ticking smoothly. He wasn't on board with Leibniz's take that God made a perfect world that needed no extra divine meddling. For Newton, evidence of God's guiding hand was all over the universe, showing that divine involvement never stopped. The balance of the solar system and the design of planet orbits seemed to show a steady hand at work. This mix of theology couldn't be disentangled from Newton's way of doing natural philosophy, even if later interpretations tried to tone it down. In his general scholium, Newton concluded by saying the real goal of natural philosophy was to discuss God based on what was observable. This wasn't just an afterthought, but showed his real belief that physics and theology were linked. Whether he was figuring out planet paths or exploring biblical prophecies, he was essentially doing theology. Part 2. The Methodology Revolution. Newton spent years fine-tuning his approach through intense intellectual challenges. After releasing his first major paper on light and color in 1672, he faced immediate backlash. Notable figures like Robert Hooke and Christian Huygens criticized both his experiments and ideas. Feeling deeply misunderstood, Newton developed a lifelong aversion to public disputes. These clashes inspired him to establish fundamental rules for scientific advancement, aiming to separate solid knowledge from mere speculation. This gave rise to what scholars now refer to as his epistemic triad. He classified ideas into three groups: proven theories, hypothetical guesses, and queries. The latter covers ideas that aren't verified but pave the way to concrete conclusions. Hypotheses can guide investigations but aren't regarded as proven truths. Newton used them as starting points for reasoning, never as definitive judgments based on observation. His method evolved greatly between the first and later editions of Principia. The initial 1687 version of Book 3 listed 9 hypotheses, but by 1713, in the second edition, Newton had streamlined it, keeping only 2 hypotheses and reclassifying the others as either rules of reasoning or phenomena. Newton's most direct statement on methodology was his 4 rules of reasoning. Rule 1 suggests accepting causes that are both adequate and true to explain phenomena. echoing his view of Occam's razor. It isn't more if less suffices. Rule 2 indicates that similar natural effects should be attributed to the same causes wherever possible. For instance, the fall of a stone is attributed to the same cause in both Europe and America, and so is breathing in humans and animals. This lets us derive universal laws from specific experiments. Rule 3 asserts that if a quality is found in all observable bodies, such as solidity, it's a universal trait. This led to treating gravity as universal, even though Newton tested only earthly and celestial bodies within sight. Rule 4, the most philosophically provocative, posits that conclusions drawn inductively from phenomena should be seen as true until new evidence suggests otherwise. This rule prioritizes experiment over speculation, grounding knowledge even when absolute certainty isn't possible. Newton believed that knowledge useful for both practice and theory could be achieved, and potential theories shouldn't derail conclusions based on evidence. In the second edition, Newton introduced the general scholium, featuring his renowned methodological claim. He wrote, "Hypotheses non fingo," a Latin phrase meaning, "I frame no hypotheses," or "I feign no hypotheses," sparking centuries of debate due to its vagueness. Newton clarified that anything not derived directly from phenomena is a hypothesis, and such hypotheses are unwelcome in experimental philosophy, whether metaphysical or physical, or based on mysterious qualities. In experimental philosophy, specific propositions emerge from phenomena and broaden into general truths through induction. This approach set Newton apart from rationalist thinkers like Descartes and Leibniz, who provided mechanical explanations for gravity. Leibniz proposed the concept of whirlpools or vortices, imaginary fluids spinning around planets to explain their motion. Newton thought this was inventing unnecessary explanations, not based on observation. He had already established the mathematical law of gravity, which adequately explained motion in space. Yet some critics argued that Newton also resorted to invention by suggesting objects could influence each other across empty space. How, they asked, could objects interact at a distance without something in between? This seemed to reintroduce mystical qualities the mechanical philosophy had supposedly eliminated. Philosophers like Leibniz found this idea offensive to their worldview, even if it worked out mathematically. Newton shot back, emphasizing that he'd proven gravity to be a real force with predictable mathematical laws. Whether this gravity traveled through mysterious means or acted directly across space was still up in the air. While privately he speculated on mechanisms like ethers, he kept those musings out of his public work, preferring to base his published findings on observable truths. This approach marked a significant change in science. Earlier, scientists aimed to uncover the causes and mechanics behind everything. Newton thought just using math to describe how things work was good enough. You didn't need to understand why gravity operates according to the inverse square law to use it effectively. This line between knowing how and knowing why later became a key theme in the philosophy of science. Newton highlighted how important it is in science to have accurate math laws describing what we see. Demanding mechanical explanations or deeper causes could be premature if things weren't fully explored yet. His idea was that detailed math descriptions should come first before chasing unsupported theories. Nevertheless, Newton didn't give up on finding deeper explanations or physical causes. His studies in optics ended with a slew of questions on the nature of light, matter, and force. These weren't final answers, but starting points for more exploration. He flirted with ideas like subtle fluids and active principles that might clarify what we observed. Navigating between these two extremes was something Newton managed throughout his career. On one side, sticking to pure empiricism could get lost in data without achieving true comprehension. On the other, pure rationalism risked crafting beautiful theories without real-world or experimental backing. Newton's approach blended solid math with reasoning shaped by observations. His math skills had to be sharp to tackle the messy realities of real-world observations. In the Principia, he used elegant geometry to derive solutions from ideal situations, then noted deviations between theory and reality. He constantly adjusted models to better match reality, a method that became a standard in mathematical physics. The process starts simply by covering the basics and gradually adds complexity to get a clearer picture. Newton demonstrated this technique in developing celestial mechanics in his Principia. His approach also touched on what's now known as error analysis and understanding uncertainty. Newton was aware that measurements came with errors and only gave rough estimates. He devised ways to draw solid conclusions from imperfect data. Acknowledging that certainty varies showed a mature understanding of empirical science. Newton's reasoning principles shaped scientific approaches for 2 centuries after his time. They impacted how scientists made inductive inferences and formulated conclusions beyond observed cases. David Hume's critique of causation and induction challenged Newton's method, while Immanuel Kant crafted his transcendental philosophy partly to unravel how Newton's science reached such comprehensive understanding. The phrase hypothesis non fingo became a rallying cry for those supporting an empirical view of science. 19th century thinkers, known as positivists, often idolized Newton as their guiding light, dismissing anything even remotely metaphysical. This was quite ironic, given Newton himself privately engaged in metaphysical, theological, and even alchemical studies. The refined image of Newton that emerged during the Enlightenment didn't really reflect his true self. Part 3. Newton's Secret Beliefs. Isaac Newton wasn't your average guy when it came to religious views. He kept his disagreement with the Church's official take on the Trinity under wraps throughout his life. Newton thought the traditional Trinity was a huge misunderstanding of what Christianity was supposed to teach. He traced this misunderstanding back to the 4th century, after the Council of Nicaea in 325 A.D. Newton's curiosity wasn't limited to science and math. He also dove deep into theological study. He wrote extensively on biblical prophecy, dissected historical texts, and traced the evolution of Christian ideas. Using a sharp eye and critical thought, he treated religious texts with the same scrutiny he applied to scientific ones. Though he shared a manuscript with John Locke that questioned the biblical basis for the Trinity, it never saw publication. Aware that his ideas were considered heretical in 17th century England, a place where such beliefs could damage your career and have dangerous consequences, he stayed quiet. Cambridge professors were required to be ordained in the Church of England, which was a problem for Newton around 1675 because he couldn't truthfully profess beliefs he disagreed with. Thanks to Isaac Barrow, his predecessor, he managed to dodge ordination requirements. From then on, Newton learned the value of keeping his theological views to himself, practicing what scholars call Nicodemism. He outwardly conformed while privately disagreeing. Newton did the church thing, showing up for services and affirming Anglican beliefs when needed, all to shield his career and work. He truly believed in one God, not a Trinity, and saw Jesus as God's Son and the Messiah, but not equal to God. This belief made him an Arian, like Arius, an early theologian whose ideas were denounced at Nicaea. To Newton, only the Father was the true God with ultimate power. Newton mingled scripture study with philosophical exploration to contest the Trinity. He couldn't find strong biblical support for it in original scriptures, noticing that many verses were later modifications. For instance, the Johannine comma in 1 John didn't appear in early manuscripts. He also saw logical issues with the Trinity. How could three separate beings be the same substance? The idea of the Father sending the Son, yet both being eternal, sounded more like a human mistake than a divine mystery. Newton thought early Christians followed a singular God, and it was Greek philosophy that influenced the idea over time, not Hebrew monotheism. Figures like Athanasius, he suggested, pushed this idea with political tactics and text alterations, a claim he laid out in a detailed manuscript critiquing Athanasius. Newton's theological take was deeply linked to his views on physics. His belief in God's oneness mirrored his theories about absolute space and time. Just like God is singular and unified, space and time are whole and indivisible. Confusing relative and absolute ideas in physics was similar to misconceptions about God. Newton saw God's omnipresence as literally forming space, with space and time being expressions of God's existence, seamlessly blending science and spirituality. This belief drove his physics, where he saw God actively ensuring the universe stayed on course. Sometimes, God even had to make adjustments to the universe, like keeping the solar system in check. Gravity, in Newton's eyes, might be more about God's active guidance than just a mechanical force, which clashed with what many Enlightenment deists thought. Deists believed God created the universe and then let it run on its own like a perfect machine. Newton found this view lacking both theologically and scientifically. He saw clear evidence of God continuously steering the universe rather than it being a self-running machine. Newton had a keen interest in Prisca Theologia, or what you could call ancient theology. He believed that God had shared the true essence of religion with Noah and the patriarchs even before Moses came along. This original belief system was pretty straightforward. Worship the one true God and live by two main rules. Love God completely and treat your neighbors kindly. Newton thought that this pure religion was what early civilizations practiced before it got distorted by priests in places like Egypt, Babylon, and Greece. Pythagoras, in his journeys, picked up genuine insights which he passed down to his followers using symbols. Newton believed ancient temples represented the heliocentric universe's layout and held significant cosmic truths. For him, this idea made him see his scientific endeavors as a revival of ancient knowledge rather than inventing new concepts. The heliocentric model, mathematical principles of nature, and correct devotion to God were just parts of the same interconnected view. Newton felt that modern philosophy had strayed from its noble roots, and he aimed to reignite that ancient wisdom. Newton's fascination with alchemy was partly driven by the quest to find hidden knowledge buried in symbolic language. He considered alchemical writings as potential carriers of truths about matter and forces, albeit in a coded form. The philosopher's stone, in his mind, might be a tangible item and a symbol for profound understanding. It wasn't just mysticism, but a discerning approach to studying ancient texts. He also worked on biblical chronology, aiming to establish exact dates for historical events, using his skills in astronomical calculations. By interpreting mentions of celestial events in old writings, he aimed to reconstruct an accurate timeline, combining his knowledge of astronomy with scriptural study for a better grasp of theology. These interests weren't isolated pursuits for Newton. They were part of a broader, unified quest. He delved into biblical prophecy to grasp God's plans for human history. He believed that books like Daniel and Revelation contained coded messages about past and future events. He created elaborate ways to link these prophetic symbols to actual historical occurrences, predicting that the distortion of the Trinity would last until the end of times. Newton's calculations suggested that true religion wouldn't make a comeback until around 2060, based on a timeline starting with Charlemagne's crowning in 800 as Holy Roman Emperor. He felt he was living in times marked by a long forecast religious decline. For him, theological efforts were just as intense and important as his scientific work, not just pastimes. Both science and theology vied for his attention, with the shared aim of understanding God's nature and unveiling divine truth. After Newton passed away, there was a dilemma about what to do with his theological writings. Publishing them might portray him as a heretic, risking his legacy, while hiding them meant burying a big part of what drove him. Eventually, they opted to keep them hidden until the 20th century. When the world finally got a glimpse of Newton's religious beliefs, they were baffled. How could the founding figure of modern science hold views that seemed so irrational? This highlighted how contemporary notions often assume science and religion should be separate or even at odds. But for Newton, they were all part of a seamless journey to uncover truths about God and creation. Part 4. The Optical Showdowns. In 1666, while still a student, Newton got his first glass prism and dove into experiments with light and color that revolutionized optics. His discoveries sparked heated debates for years, shaping how he engaged in scientific discussions. At the time, people believed white light was pure, and any colors represented distortions. According to this idea, glass adulterated white light, producing colors, implying more glass would distort it further. Newton shattered this notion with his simple experiments. He passed white sunlight through a prism, splitting it into a colorful spectrum. Then he cleverly used a second prism to merge these colors back into white light without any loss. This revealed that colors weren't distortions of white light, but its basic parts. White light was a combination of various colored rays traveling together. The prism didn't change the light, but simply separated what was already present. Each color refracted at a unique angle when moving through glass. Newton figured out that light's different forms matched different colors. For example, red and blue light refracted differently. Each color had its specific refraction angle when transitioning from air to glass, outlining the spectrum of white light's components. Newton shared these revelations with the Royal Society in 1672 with his paper titled Letter Containing His New Theory About Light and Colors. He argued that his experiments provided solid evidence, backed by geometric evidence, rather than mere speculation. Robert Hooke, a leading expert in optics in England, immediately took issue with Newton's theory. Perhaps feeling challenged by the younger scientist, Hooke offered several objections. He believed Newton leaned towards the idea of light being particles, known as corpuscles, while Hooke saw light as waves, putting Newton's theory directly in his sights. Newton was frustrated, believing Hooke missed the essence of his work. Newton stressed that his findings stood on their own, regardless of light being particles or waves. Christian Huygens also critiqued Newton, though in a calmer and less confrontational way than Hooke. Building on earlier work, Huygens developed an advanced wave theory of light, explaining reflection and refraction. He described how each part of a wavefront, as it moved forward, generated new wavelets spreading out like ripples. The debate between particle and wave theories continued for over 200 years, with Newton backing the particle theory and Hooke and Huygens supporting the wave theory. Each theory explained some phenomena well, while others were less clear. Newton's particle model explained things like straight-line movement and sharp shadows. He argued if light were a wave, it should bend around obstacles like sound does, as sound can travel around corners, but light travels in straight lines. Observations of light bending through tiny openings later challenged this view. Newton's particle theory considered reflection as particles bouncing off smooth surfaces. Different sizes and shapes of particles could explain different colors, since they'd refract differently. For refraction, Newton thought particles sped up in denser materials, causing them to bend towards the normal. This idea implied that light should travel faster through denser materials, but later it was proven false. However, Newton noticed some things needed wave-like explanations. For instance, soap bubbles display colorful interference patterns because of their thickness. Light either reflects or passes through these thin films without obvious changes. So, Newton proposed that these tiny light particles, or corpuscles, had phases that made them either reflect or penetrate the film. He thought maybe these particles created waves in the ether as they moved, which could catch up and cause these phases. This theory was a blend, keeping the particle concept while introducing wave ideas. It showed how Newton was willing to update his ideas when the evidence required it. Optics, published in 1704, was Newton's significant work on light. Unlike the dense, math-focused Principia, it was written in English and was more accessible. The book described experiments people could perform themselves and carefully drew conclusions from them. It also posed lengthy questions, inviting more exploration. This format allowed Newton to speculate more freely than he did in Principia. He pondered whether light particles varied in size for different colors and if ether differences might explain optical phenomena. These weren't final answers, just concepts to explore further. The impact of optics on science was distinctive, unlike Principia, despite its lighter mathematical approach. It became a guide for merging observations with theoretical thinking in experiments. Newton's questions illustrated guiding research without adhering to strict beliefs. David Hume even used this method as a template for his philosophy. The conflict with Hooke deeply affected Newton, making him avoid intellectual disputes and delay some publications. He only allowed optics to be published in 1704, after Hooke passed away. His reluctance to engage in controversy meant many of his ideas stayed unpublished for years. In 1801, Thomas Young's double-slit experiment provided strong support for wave theory. When light goes through two slits, it creates a pattern of light and dark bands on a screen, something that particle-only theories couldn't explain. More tests in the 1800s backed wave theory with discoveries about interference, diffraction, and polarization. Even though Jean-Baptiste Biot initially attempted to explain polarization with particles, mounting evidence favored waves. By the late 19th century, wave theory mostly edged out Newton's particle idea. But then quantum mechanics came along, showing that both were partly right about light's dual nature. The early 20th century photoelectric effect unexpectedly revived the particle concept. Light ejects electrons from metal in ways that wave theory couldn't explain. Einstein proposed that light consists of energy packets, or photons. With this, light exhibited both particle and wave behaviors, depending on the experimental setup. In modern physics, this wave-particle duality is crucial to quantum mechanics. Light behaves like waves in interference and diffraction tests, but like particles in the photoelectric effect and Compton scattering. Traditional wave and particle ideas both fall short of entirely explaining quantum phenomena. Although incomplete, Newton's particle theory anticipated parts of today's photon theories. His intuition about light having discrete entities moving in space captured a piece of the puzzle. The old debate between Newton and Huygens wasn't resolved by classical physics. They were both right and wrong in ways they couldn't have predicted. Part 5 dives into the Principia and Universal Mathematics, a visionary work that revolutionized science. Published back in 1687, The Mathematical Principles of Natural Philosophy might just be the most influential scientific text ever. Newton came up with a mathematical system that tied together the mechanics of Earth and space through universal laws. He showed that the force that makes apples fall is the same one that keeps planets revolving around the sun. This was a huge leap forward intellectually, reshaping our approach to natural philosophy. The origins of this work date back to conversations with Robert Hooke around 1679–1680. Hooke proposed that two forces influence planetary motion, one that keeps planets moving along a straight path due to inertia, and another that pulls them toward the sun. The mix of these forces, guided by exact mathematical rules, results in orbits. Hooke also mentioned that the central force gets weaker with the square of the distance from the sun. This inverse square law was also on the minds of Christopher Wren and Edmund Halley. But they couldn't use this idea to explain Kepler's planetary motion laws, as they were missing the necessary math tools and insights for that. Newton, however, had figured out much of the math years earlier, but hadn't published it. In 1684, Halley visited him and asked about the link between the inverse square force and elliptical orbits. Newton confirmed he had previously done the calculations and, despite not finding his old notes, promised to rework the demonstration. This led to Newton's most productive creative period, resulting in the Principia in less than 2 years. The project expanded to cover an extensive mathematical study of motion. Book 1 presents General theorems about motion under central forces using geometric methods. Book 2 explores motion through resisting mediums and disputes Cartesian vortex theories. Book 3 puts the mathematical system to the test with our solar system, deriving planetary paths from observed data. This was groundbreaking, merging abstract math with real astronomical events. Newton showed how to deduce universal gravitation's existence and form from Kepler's laws, and even predicted some tweaks to Kepler's models due to planetary gravitational interactions. Principia kicks off by defining essential ideas like mass, momentum, and force, giving precise mathematical definitions to terms that used to be ambiguous. It follows with the famous scholium on absolute space and time, setting Newton's metaphysical stage. Then come the three laws of motion, which are the foundation for all the arguments that follow. Newton's first law about objects staying in their state of rest or uniform motion unless acted upon wasn't his own invention, but built on Descartes and Galileo's work. Still, Newton made it foundational and expressed it clearly in mathematical terms. The inertia principle explained why planets keep moving without needing constant force. The second law states that changes in motion are proportional to the applied force and occur in the same direction. This became the crucial link between force and acceleration, now written as force equals mass times acceleration in physics. Newton described this geometrically, considering momentum changes over tiny time intervals. The third law, Newton's own creation, states every action has an equal and opposite reaction. If one body applies force on another, the second pushes back with the same force. This law was key to understanding complex systems, ensuring internal forces balance out to keep total momentum steady. With these principles, Newton used geometry to derive several theorems. He proved that an inverse square central force leads to elliptical orbits with the focus at one point. He also linked the orbital period to its distance, perfectly aligning with Kepler's third law. These conclusions not only confirmed Kepler's findings, but grounded them in basic principles. Book 3, The System of the World, applied these theoretical math ideas to real space phenomena. Newton began with 6 examples outlining observed patterns in planetary and lunar behaviors. So, Newton used his thinking skills to crack the code of universal gravitation, figuring it all out from patterns he noticed. His argument was a blend of solid math and careful observation of the natural world. He proved that the moon's pull towards Earth matched the gravity we feel on the surface. After calculating the force needed to keep the moon in its orbit, he discovered it was just like Earth's gravity, connecting the dots between earthly and cosmic forces. The old belief that forces on Earth and in the heavens were different quickly crumbled. Newton showed that planets and moons all followed the same rule, the inverse square law, including the satellites of Jupiter and Saturn and planets circling the Sun. This suggested that one force spread through all of space, steering everything in the universe. Newton called this force gravitation, linking it to the masses of the objects involved. His equation explained that the force was the product of two masses divided by the square of the distance between them. This was a shift from vague ideas about how planets moved to a clear law. Every little bit of matter pulled on every other bit by this simple mathematical rule. The big insight was realizing there's one fundamental force driving all we physically see. Newton liked starting with simple examples, adding complexity along the way. He first tackled how two bodies interact with just gravity, then factored in complications like additional bodies or uneven mass distribution. Each step brought his calculations closer to real life. He even worked out how the sun affects the moon's path and how tidal forces make Earth wobble on its axis. He noted how Jupiter and Saturn slightly tweaked each other's paths through gravity. These detailed adjustments allowed him to make precise predictions from the chaos of reality. In the Principia, he also nailed down how tides worked using gravity, calculating how the moons and suns pull-shaped ocean tides, and his math matched the tidal patterns people observed. But Newton knew his theory of gravity didn't cover everything. Sure, gravity existed and followed a clear math rule, but he didn't know why it acted like it did without physical contact between objects. The idea that forces could act over empty space was tough for many to accept. Critics argued it conflicted with the notion that objects move other objects by contact. Figures like Descartes and Leibniz believed matter needed to touch to have an effect. The notion of attraction over a gap seemed a little spooky, like old mystical thinking. Newton's fans found defending this idea tricky due to philosophical challenges. Newton argued that understanding how gravity worked mathematically should be enough for natural philosophers. He was content with gravity being real and predictable. He suggested possible causes like ether pressure, but avoided speculation without evidence, famously stating he didn't make up hypotheses. The math was rock solid, even if the mechanics were hazy. The Principia essentially launched math-based physics as a distinct field with its rules and standards. Before Newton, natural philosophy was mostly about abstract ideas or geometry without real tests. He demonstrated how to build mathematical frameworks based on observation and test their predictions. This approach paved the way for all disciplined science that followed. His contributions didn't just transform physics, but also influenced philosophy and intellectual thought. His work proved that human intellect could unlock nature's great mysteries. During the Enlightenment, there was a strong belief in the power of reason, much of it fueled by Newton's incredible discoveries. People in many fields aspired to be the Newton of their own disciplines. Part 6. Chasing the Alchemical Dream. Isaac Newton was completely absorbed in alchemy and chemical processes, putting as much energy and care into them as he did in his studies of optics and math. Over the years, he filled up notebooks, painstakingly copied ancient alchemical texts by hand, and undertook risky experiments in his lab, all in an effort to untangle the active principles of substances. Back then, the line between alchemy and chemistry wasn't really clear. Both were ways to explore how matter acts and changes through observation and experiment. Alchemy was more than just trying to switch lead into gold. It was also linked to practical crafts like metallurgy, medicine, and dye-making. Newton's alchemical works led him to understand the subtle forces at play in tiny realms of matter. He thought particles could move due to invisible attractions and repulsions, much like gravity, but on a smaller scale. These hidden forces, he believed, could explain chemical reactions unlike the mechanical philosophy of his time. Philosophers like Descartes saw the world as a collection of machine parts fitting together, but that did not account for why some chemicals seem to have a natural attraction to each other. Why did acid manage to eat through certain metals while it left others alone, even if they seemed quite alike? Newton speculated about unseen forces controlling such behaviors in chemistry, similar to gravitational pull, but in a different arena. Alchemy, with its hands-on insights, could possibly unravel these mysteries. In his work, Nature's Obvious Laws and Processes in Vegetation, Newton approached plant growth from an alchemical angle, suggesting that active principles within plants drew the required particles from their surroundings. This acted like a type of chemical reaction, where specific elements would naturally come together. Newton even pursued the legendary Philosopher's Stone, aiming to uncover the mythical material believed to transform metals and offer wisdom, not as a foolish dream, but as an earnest scientific quest of that time. If changing these particle forces could alter a substance's nature, transmutation might not be impossible. Alchemists typically wrote in coded and symbolic language to protect their secrets, convinced that ancient wisdom lay hidden beneath these layers. Newton believed that these ancient alchemical writings contained true chemical insights, cloaked in enigma. This curiosity also connected with his larger aim of reviving ancient wisdom, known as the Prisca Theologia. In keeping with his secretive nature, Newton kept his alchemical studies under wraps for his entire life. Only after his passing did people find his lab filled with somewhat unconventional tools and notes, revealing an intense hands-on approach running alongside his well-known mathematical work. Newton's interest in active principles linked closely to his broader scientific theories. He imagined that gravity itself could be considered an active principle, implying that matter might have intrinsic tendencies beyond just inertia. These musings challenged the existing belief that everything could be reduced to basic mechanical interactions. In later versions of his work on optics, he even wondered out loud whether particles had natural attractive forces when in close proximity. Could these unseen forces be the key to decoding chemical reactions, surface tension, capillary action, and other fascinating natural behaviors? Nature's driving forces operate on various levels, merging chemistry and physics through common principles. The idea was that nature relied on the attraction and repulsion of tiny particles, with these forces changing depending on distance, much like how gravity works. Chemistry, heat, electricity, and magnetism all tied back to particle interactions. This concept hinted at what would become modern physics, where forces are unified through mathematical field theories. Newton wasn't just focused on optics, he was equally detailed in his alchemical pursuits, taking a scientific approach by closely observing, adjusting variables, and documenting everything. His scrutiny of alchemy was as precise as his investigation into prisms and lenses, though alchemy was shrouded in mystery and symbols. Some believe Newton's alchemical studies directly influenced his ideas on gravity, as the notion of matter having active principles borrowed from chemistry might have suggested non-mechanical forces in physics. The Philosopher's Stone represented the most dynamic form of matter, similar to how gravitation implies an inherent force in all matter. However, others point out the gap between Newton's public scientific works and his private interest in alchemy. In Principia, his mathematical masterpiece, alchemical thoughts were absent, and he deliberately separated firm mathematical proof from speculative chemical ideas. Both perspectives help us understand the complex nature of Newton's intellectual endeavors. His mind seamlessly navigated through mathematical mechanics, optics, chemical processes, and theology, finding connections that later generations saw as separate fields. In Newton's mind, this unity existed even if not explicitly stated in his work. It wasn't until the 20th century that Newton's alchemical interests came to light with the discovery of his manuscripts, altering how scholars viewed his legacy. This revelation showed Newton not just as a rational thinker of the Enlightenment, but as someone delving into both nature and spirituality. Modern chemistry ended up validating some of alchemy's ideas while discarding others. Nuclear reactions can indeed result in transmutation, but the mythical philosopher's stone is a different story. Chemical reactions involve atomic forces beyond mere mechanical interactions. Newton's concept of active principles controlling matter proved insightful, and his thorough experimental methods left a lasting mark on chemistry, despite his less successful theories. The practice of detailed experimentation with careful documentation became standard. Chemists, adopting Newton's mathematical approach, began seeking quantitative laws in chemical reactions, thus distinguishing his effective methodology from his less accurate theories. Part 7. Ancient Wisdom and Newton's Journey. Newton genuinely believed that ancient civilizations had a profound understanding of nature and the divine, a wisdom that had been muddled or lost over time. His interest in ancient cultures was more than just romantic. It was central to his intellectual pursuits. He spent years diving into ancient texts, comparing mythologies, and reconstructing what he termed Prisca Theologia. This concept was about the original truths God shared with Noah and the earliest patriarchs. Building on Renaissance traditions passed down to him, Newton reshaped these ideas. Influential thinkers like Marsilio Ficino and Giovanni Pico della Mirandola argued that even pagan philosophers had glimpses of divine knowledge. They connected the teachings of Plato, Pythagoras, and Hermes Trismegistus to biblical revelations. Newton went a step further, grounding this idea in evidence and historical analysis. He saw the original religion as being rooted in two simple commandments, later reinforced by Christ. Love God completely and love your neighbor as yourself. According to Newton, this pure monotheism started with Noah and passed down through Abraham, Isaac, Jacob, and Moses to the Israelites. Other cultures, however, distorted this pure belief into idolatry, though fragments of truth remained. In his work, Theologia Gentilis Originis Philosophicae, Newton explored these distortions. Ancient priesthoods transformed the worship of the one true God into complex polytheistic systems. Yet, traces of original monotheism persisted in certain philosophical traditions and mystery religions. Newton was particularly intrigued by the idea that Pythagoras gained true insights during his travels in Egypt and Babylon. Newton believed the Pythagorean system contained genuine natural philosophy, shrouded in symbols. Pythagoras supposedly taught that Earth revolved around a central fire, an early nod to the heliocentric model Copernicus would later advocate. Newton thought ancient philosophers knew the true structure of our solar system. He also believed that ancient temple designs reflected a deep understanding of cosmology. Solomon's temple, and those dedicated to Vesta, for example, featured circular designs with central sacred fires. Newton saw these as representations of the heliocentric system, with the sun at the center. For Newton, religious rituals and natural philosophy were originally one. Temples, he believed, were models of the universe, revealing that the cosmos was God's grand temple, with architectural details holding scientific significance for those who could decipher them. This is why ancient wisdom often seemed buried in cryptic allegories. Newton's Prisca Theologia concept influenced his approach to alchemy and science. He thought alchemical texts concealed ancient chemical knowledge in dense, symbolic language to protect it from corruptions. By unlocking these codes, one could rediscover lost experimental methods and theories. Newton felt his work was about restoring lost knowledge, not forging new paths. He aimed to revive Prisca Sapientia, the ancient wisdom that linked the natural and divine realms. He believed modern philosophy fell short compared to the achievements of ancient masters and needed a restart. His Principia sought to revive the mathematical natural philosophy once held by Pythagoras. In his chronological studies, Newton aimed to establish accurate timelines for ancient history, using astronomical clues, like celestial events mentioned in old records. By identifying the timing of these cosmic occurrences, Newton hoped to accurately date historical timelines, revealing the true development of ancient cultures and interactions. Newton disputed traditional dating of Egyptian and Greek history, proposing they were not as ancient as assumed. By revising these timelines, he demonstrated that all ancient wisdom ultimately traced back to biblical patriarchs, reaffirming the primacy of Hebrew revelations over supposedly ancient pagan traditions. Newton really got into studying mythological traditions from lots of cultures, looking at how they all shared some common roots. He showed how the same basic stories popped up in Greek, Egyptian, and Near Eastern myths, even though they had their own twists. These resemblances suggested there was one original source that each culture tweaked. By lining up different myths, Newton found historical ties between ancient peoples and how they passed along knowledge. He thought Phoenician sailors were the ones spreading this ancient wisdom via trade routes, sharing info on astronomy, religion, and philosophy around the Mediterranean. This could explain why cultures far apart had things in common, despite seemingly having no direct contact. It was like ancient globalization happened through these trade connections. Newton also dug into the secret practices of ancient mystery religions, looking at how they protected knowledge through initiation rituals. The Eleusinian mysteries and other similar groups kept their wisdom under wraps, slowly revealing it to new members. This way, traditions stayed pure. Newton's habit of keeping key ideas to himself was inspired by this old practice. He believed deep truths shouldn't be shared with folks who weren't ready to get them. By using the Pythagorean method of putting deeper meanings in simple comments, Newton found his way. His general scholium was aimed at readers who could read between the lines. This allowed his works to connect with different audiences, from everyday readers uncovering math proofs and experiments to those spotting theological ties and ancient wisdom connections. Newton expertly used intentional ambiguity to speak to many. His Prisca Theologia framework closely tied his natural philosophy with his anti-Trinitarian beliefs. He thought pure monotheism was the original religion, later confused with Trinitarian ideas during the 4th century. Similarly, early natural philosophy acknowledged mathematical laws and a heliocentric universe, which lost favor over time. Newton wanted to bring both religion and science back to their original purity through deep study and hands-on work. He believed he was living in a time of expected restoration, getting closer to fulfillment. While the Protestant Reformation had started bringing back true religion, it wasn't all done yet. Newton saw his work in natural philosophy as part of a big movement to restore ancient wisdom. For him, both science and theology were crucial parts of God's plan to reveal truth to humanity. Newton didn't think he was a revolutionary departing from tradition. Instead, he viewed himself as bringing back lost knowledge. He aimed to recover and refine this ancient wisdom for future generations. Modern scholars debate how much Newton's Prisca Theologia mattered. Some think it was just a side interest, unrelated to his scientific work, while others believe it was central to his motivation and methods. Evidence suggests it played a big role in how Newton saw himself and his intellectual purpose. This framework also matched wider cultural beliefs of the time about knowledge and history. Many 17th century thinkers believed human learning had declined since ancient times, and that progression meant retrieving lost insights, not finding new ones. Newton's Prisca Theologia fit right in with these views, but he chased these ideas with more passion and focus than others. His calculations and mythological comparisons went way beyond a casual hobby. Rebuilding ancient wisdom traditions was a major effort for Newton, not just something he dabbled in. Part 8. Impact and Legacy. Newton's ideas didn't just shake the foundations of physics and math, they also drastically transformed philosophy. During the Enlightenment in the 1700s, every major thinker had to grapple with the aftermath of his work. His approach, his universe view, and his mathematical achievements laid the groundwork for 18th century philosophical thought. To truly grasp this period, Newton's philosophical influence can't be ignored. It goes beyond his scientific accomplishments. John Locke, who knew Newton personally, was hugely influenced by him, and their philosophical views shaped each other. Locke's belief in empiricism emphasized sensory experience as the starting point for knowledge, moving away from Descartes' notion of innate concepts. This aligned perfectly with Newton's practical methods and his doubts about purely rational metaphysics. Both believed that theories should be deeply rooted in careful observation. However, Locke also recognized that sensory experience alone had its limits in understanding nature. He made a distinction between primary qualities, like size and motion, and secondary qualities, such as color and taste. Primary qualities were seen as inherent to objects, while secondary ones depended on perception. This distinction aimed to merge mathematical science with empiricist thinking. Newton's ideas about space, substance, and the nature of reality influenced Locke. He found himself wrestling with the idea of whether space was a substance, a property, or just a relationship. Newton's concept of absolute space offered one possible answer, though Locke never fully embraced it. Their discussions highlighted their ongoing dialogue about deep questions of metaphysics and knowledge. George Berkeley crafted an idealist philosophy in response to Newton's mechanics and Locke's empiricism. He threw out the idea of material substance, arguing that only thoughts and ideas really exist. He believed physical objects were merely collections of sensory perceptions in the mind. His bold stance aimed to resolve the gap between appearance and reality that troubled Locke. Berkeley also challenged Newton's notion of absolute space and calculus, criticizing them philosophically and mathematically. He argued that space existing beyond perception was practically meaningless. Berkeley took issue with calculus's reliance on the notion of infinitesimals, arguing that it didn't make logical sense. His critiques exposed real problems in Newton's theories, though his system remained widely successful. David Hume sought to apply Newtonian methods to the study of human nature and ethics most comprehensively. In his book, A Treatise of Human Nature, he tried to bring the experimental method to moral philosophy, aspiring to do in psychology and ethics what Newton had done in physics. This involved identifying patterns in human thought and behavior to form general principles. Hume's examination of causation directly interacted with Newton's methods and their philosophical bases. Newton claimed gravitational law was derived through induction from observations, but Hume argued that induction itself doesn't have a strong rational basis beyond habit and tradition. We can't logically prove that future cases will align with past observations. For Hume, causation was simply the regular occurrence of events in our experience. We notice certain events tend to follow others and form expectations based on that, but we never see a direct, necessary link between causes and effects. The notion of causal power is more of a mental construct than an observable fact. This skeptical view posed a philosophical challenge to the Newtonian model. If induction doesn't have a rational foundation, then Newton's conclusions from observation are on shaky ground. The laws of motion and gravity could become as uncertain as our everyday assumptions. Hume's reflections led to what Kant later described as a crisis, awakening him from his dogmatic slumbers. Nonetheless, Hume admired Newton's successes and never intended to undermine them. He distinguished between the practical certainty needed for life and science versus philosophical certainty. Newton's methods were highly effective, even if their philosophical justification was uncertain. We can trust induction, even if we can't fully explain its effectiveness. Continental philosophers engaged with Newton's ideas differently from the British empiricists. Back in the 1730s and 40s, Voltaire was one of the biggest cheerleaders for spreading Newton's ideas in France. He penned elements of Newton's philosophy to break down the complex principia and optics for educated people who weren't math experts. To Voltaire, Newton was the ultimate champion of reason, standing against religious superstition and rigid philosophies. Meanwhile, a brilliant woman named Émilie du Châtelet crafted the authoritative French translation of the Principia, which is still referenced today. A gifted mathematician, she truly understood Newton's work, both its technicalities and its philosophy. Her annotations made the tough parts easier to grasp by connecting Newtonian physics with Leibnizian metaphysics, showing how insights from different philosophical traditions could be combined. The correspondence between Leibniz and Clarke from 1715 to 1716 played a key role in philosophical debates later on. Leibniz took issue with Newton's idea of absolute space, saying it contradicted the principle of sufficient reason. Clarke, defending Newton, talked about space in relation to God's omnipresence and influence. This exchange shed light on fundamental rifts between rationalist and empiricist thinking. These debates were pivotal throughout the 18th century, influencing thinkers all over Europe and impacting Kant in the 1770s as he grappled with concepts of space, time, and causation. Kant saw flaws in both rationalist metaphysics and empiricist skepticism, as neither could completely explain the knowledge about nature achieved by Newtonian science. His critical philosophy tried to bridge the gap that Newton's work represented between rationalists and empiricists. Kant believed space and time weren't objective realities or just empirical relations, but ways we organize experiences, meaning they were vital but not independent from human thought. He argued Newton's laws were valid because they mirrored how humans must structure their experiences. According to Kant, causation wasn't something you observed directly like Hume thought, nor was it derived from pure reason as rationalists claimed. Instead, it was a concept our minds needed to make sense of things, allowing for objective experiences. This view accounted for Newton's scientific success and showed the limits of what physics could reveal about the true nature of reality. Kant's reinterpretation made waves in 19th-century German philosophy, separating Newton's physics from his ideas about absolute space and divine influence. This allowed the scientific community to keep Newton's laws while letting go of his theological and metaphysical beliefs, supporting the growing secular scientific mindset of the 1800s. Meanwhile, science kept advancing by applying Newton's methods to new areas. Lagrange and Laplace developed analytical mechanics, using innovative mathematical approaches to put a new spin on Newtonian physics and accurately predicted planetary movements. Laplace famously boasted that celestial mechanics could function perfectly without God needing to intervene. This change in perspective flipped Newton's original goals, since he saw physics as an avenue to understanding divine actions. The Enlightenment recast Newton as a champion of rational secular inquiry, often ignoring his theology, alchemy, and interest in prophecy to concentrate solely on his mathematical achievements. As a result, Newton's image turned more into myth than historical truth. In the 19th century, his mechanics were applied to domains like electromagnetism, thermodynamics, and statistical physics. Maxwell's equations for electromagnetic fields followed Newton's approach of using math to generalize from experiment. The kinetic theory of gases employed Newtonian mechanics to explain molecules and thermodynamics. Successful theories took Newton's model of melding math with empirical data. Still, some anomalies defied Newtonian explanations. Mercury's path didn't align with gravitational predictions, and the constant speed of light defied Newtonian relativity. Atomic behavior demanded discrete energy levels, challenging classical mechanics. Then, Einstein's theories of relativity in 1905 and 1915 revolutionized things, moving away from Newtonian mechanics altogether. Space and time aren't set in stone. They shift based on who's watching and come together into what's called space-time. Gravity isn't really a force. It's more like space-time getting bent by mass and energy. These concepts shake up Newton's basic ideas, although his laws still serve as trustworthy approximations. Then, in the 1920s, quantum mechanics took it a step further, seriously challenging Newtonian certainty. On super tiny scales, randomness plays a role in physical processes, not just ignorance about starting points. Particles can't be pinned down to exact locations and speeds simultaneously, clashing with classical views. The math for quantum theory is nothing like Newton's mechanics. But even with these major changes, Newton's overall approach to science stuck around. Physics still blends math theory with experimental testing, much like Newton did. We express laws as differential equations to define possible behaviors. Theories thrive by making super-precise predictions that we either confirm or debunk through observation. The philosophy of science is still wrestling with questions that Newton's work sparked, like how observations decide which theory to choose when many fit the data, or what makes a scientific idea legit versus speculative metaphysics. Newton's hypotheses non fingo idea remains relevant today in discussions of scientific realism and methodology debates. Part 9. The Strains and Boundaries. Newton's theories had some deep conflicts he couldn't quite resolve, and later advances in science only highlighted them more. Even though he claimed his findings came purely from observable facts, he leaned heavily on metaphysical ideas like absolute space, something no one can actually see. From the get-go, there were critics pointing out this gap between his talk of empiricism and his actually more rationalist methods. Newton's physics couldn't stand without the idea of absolute space. To tell apart real acceleration from just shifting positions, his laws of motion needed it. Without absolute motion, his second law wouldn't hold up, because all movement would be just about which reference point you pick. Newton himself admitted that absolute space and time couldn't be directly measured. He tried to sidestep this by saying that forces could show us real acceleration. He suggested actual changes in motion were caused by forces acting on objects, which we could spot through visible signs like what happens to water in a spinning bucket. But this line of thinking has holes, as it presumes you can already tell real motion from apparent motion before pinpointing forces. The well-known bucket experiment was meant to show absolute rotation independently of other reference points. As the bucket spins, the water inside eventually spins too and forms a concave shape. Newton said this concave shape was proof of true rotation, showing it was relative to space itself and not nearby objects. In the late 1800s, Ernst Mach questioned this approach and offered other interpretations. Perhaps the water forms that shape because it's spinning in relation to distant stars. What if instead the stars were swirling around a still bucket? The same thing might happen. This idea put a dent in Newton's claim about demonstrating absolute motion. Later on, Einstein's theory of general relativity aligned with Mach's thinking, suggesting that inertial effects depend on how matter is spread out across the universe. Mass influences the curvature of space-time, setting the local inertial conditions. There's still a split between inertial and non-inertial motion, but it's dynamic, not fixed. Space isn't just a rigid entity that independently dictates acceleration. Newton's theory of gravity also stumbled when it came to the notion of action at a distance, something proponents of Cartesian and Leibnizian philosophies called out. How could the sun tug on Earth from 93 million miles away with no physical connection? Mechanical philosophy demanded direct contact to explain causes, and gravity seemed to break the rules, bringing back concepts that medieval philosophy had long discarded. Newton saw this issue, but felt proving gravity and its laws with mathematics was more vital than meeting mechanical expectations. He even privately mused about a kind of ether that might mechanically transmit gravity, but decided against publishing those thoughts without experimental evidence. This choice to embrace the unknown over conjuring unsupported explanations opened him to criticisms of inconsistency, since he asked others for mechanical reasons, but exempted his gravitational force from needing one. Leibniz and Huygens argued that vortex theories at least tried to offer mechanisms, even if speculative. Newton's approach seemed to forego the search for true physical explanations. Ultimately, Newton's decision to accept mathematically defined forces without requiring mechanical backing proved to be right. Modern physics shows electromagnetic forces also act through empty space without direct material links. Quantum field theory describes these forces via field equations instead of tangible particle interactions. The hunt for mechanical explanations was too limiting for basic physics. Yet, unlike Newton's gravity, today's forces travel at a finite speed, not instantaneously across any distance. When source masses change, their effects on far-off objects take time to reach them at light speed. Newton's idea of instant action at a distance wasn't just puzzling, it turned out to be wrong. The particle theory of light pokes a giant hole in Newton's physics. Newton argued convincingly for light being particles, not waves. Light zips in straight lines and creates sharp shadows, quite unlike sound, which sneaks around corners. Bouncing off surfaces, light behaves like elastic particles crashing into them. But Newton's theory stumbled when dealing with colors in thin films. Why does light sometimes reflect off soap bubbles, sometimes passing through them, seemingly at random? Newton proposed that these particles had a fickle nature, sometimes bouncing off, sometimes passing through, mixing wave-like characteristics with a particle idea. In 1801, Young's double-slit experiment blew a big hole in the particle theory. It showed interference patterns of light with alternating bright and dark bands, clearly a wave trait. Particles can't create those patterns when they pass through two slits. By the mid-1800s, scientists leaned fully toward the wave theory in optics. Yet, around 1900, the photoelectric effect unexpectedly swung the pendulum back toward particles. Light popped electrons off metals, a phenomenon wave theory couldn't neatly explain. Einstein showed that treating light as tiny packets of energy fit the bill. The modern concept of photons ended up vindicating parts of Newton's ideas, even if his overall theory fell short. Eventually, wave-particle duality outshone both theories, revealing that particles and waves don't encompass quantum objects entirely. Light shows wave or particle features depending on the test. Newton and Huygens both captured part of the truth, but missed the full picture. At the quantum level, nature doesn't abide by old-school ideas. Newton's approach oscillated between careful observation and bold theorizing. Though he claimed to deduce from observations, avoiding wild guesses, his universal gravitation idea was a daring hypothesis beyond earthly and visible cosmic testing. Applying it to all the cosmos was a huge theoretical leap. Who's to say there weren't countless exceptions unobserved? Newton justified this sweeping assumption with Rule 3, but that wasn't from observations. It was a methodological stance for exploring nature. David Hume later called out induction's weak spot. Consistent observations don't prove future cases will follow suit. You can't use induction to justify itself without going in circles. Newton's sweeping claims from limited observations lacked ironclad certainty. The philosophy behind induction remains a puzzle, even if it's practically essential in science. We keep trusting it because it works, not because we've nailed down its philosophical justification. Newton's method excelled in practice, even if its logic had cracks. This mismatch between success in practice and shaky philosophical underpinnings is alive in science today. Newton's religious beliefs also clashed with his published scientific stance. He thought God actively kept cosmic order through direct involvement. Yet, his public work painted nature as running on mechanical, mathematical rules. How divine tinkering fit with natural law wasn't clear-cut. If God had to adjust planetary paths, it meant nature's laws aren't self-reliant. Leibniz argued that needing divine tweaks meant an imperfect creation. On the flip side, laws being enough seemed to limit God's role to just creation, like deists believed. Newton wanted God's active hand without undermining law's inherent order. His controversial religious ideas added another layer of complexity, which he kept under wraps. The general scholium hints at Arian theology, clear only to those in the know. Newton managed to both make physics accessible while embedding hidden, unorthodox religious beliefs for the initiated. This dual approach reflects his balance between intellectual honesty and a survival instinct. Newton's writings on theology and alchemy often got sidelined, leading to a somewhat unbalanced view of his contributions. Enlightenment thinkers painted him as the ultimate symbol of pure scientific reason, free from any religious influence. However, Newton actually devoted more time to theology and alchemy than to his work in physics. His big idea of merging these disciplines ended up being separated into clashing parts. Modern physics has let go of many of Newton's original ideas, but still values his approach to scientific inquiry. The concepts of absolute space and time have been replaced by relativity's space-time framework. Gravitational force is now understood as the curvature of space-time. The certainty of deterministic pathways has been replaced by the probabilities of quantum mechanics. Despite these changes, the mathematical physics Newton pioneered is still the foundation of modern science. The conviction that nature operates through precise mathematical principles remains crucial, even as theories evolve. The current scientific method of making hypotheses and testing them traces back to Newton, despite the limitations of his own theories. Part 10. To really get Newton, you have to see how all his varied interests fit together in a big picture in his mind. For him, boundaries didn't really exist between things like physics, theology, alchemy, and history. He saw them all as different routes to discover God's nature and plans through the world around us. Whether it was natural philosophy, Bible study, or alchemical experiments, they were all just ways of chasing the same truth. Newton believed God left clues about divine wisdom in several books, each requiring its own way of being read. In the book of nature, God's power and intelligence came through math and the orderly function of the world. The book of Scripture unfolded God's plans for humanity with its stories and prophecies. Ancient philosophical and alchemical texts held fragments of ancient revelations. If you looked the right way, these three sources pointed to the same truths. Natural philosophy revealed the math behind motion and forces. Theology worked to uncover pure monotheism from beneath layers of Trinitarian belief. Through alchemy, you grasp the active principles behind matter's transformations, beyond mere mechanical beginnings. The concept of prisca sapientia bridged these areas, all tracing back to divine revelation. Newton believed God revealed these truths to Noah and the patriarchs, with their offspring imperfectly passing them down. For him, the task was to clean up and restore these traditions to their original form of unified knowledge. His stance against the Trinity wasn't a side interest. It was a crucial part of his big vision. To him, the Trinity was just as corrupt as medieval misunderstandings of natural philosophy. As scholastic Aristotelian views muddled true natural laws, Trinitarian beliefs obscured the clear truth of monotheism. Both needed rebooting by stripping away the added fluff. Newton's view of God as completely unified and present everywhere shaped his physics. Because God is everywhere, he forms the very makeup of space with his eternal presence, turning space into a divine quality rather than just a dimensional field. Space's unity reflects God's undivided nature. Time, with its absolute flow, showcases God's endless existence, organizing every event. God sees past, present, and future in one glance, while we live time moment by moment, pressing forward with no rewind. This absolute time provides the backdrop for all change and motion. Newton even speculated gravity might be God's direct action, not just a force moving through matter. God keeps the universe intact by dragging all objects toward each other. The inverse square law math explains how God manages the planet's movements. What we call natural law is actually God's will, acting consistently. Newton had faith that mathematical laws were universal, relying on God's rational and unwavering nature to ensure divine actions remained consistent everywhere. These same laws applied throughout the vastness of space because one God ruled it all. As such, mathematical natural philosophy offered a glimpse of God's rational character imprinted on our world. Newton turned to alchemy to discover active principles to fill the gaps left by pure mechanics, which saw matter as inactive. Pure mechanics couldn't explain things like chemical reactions or life processes. With active principles, matter could selectively combine in ways pure mechanics couldn't achieve. These principles might be God's creative acts at a tiny level. The philosopher's stone represented matter at its most energized and perfected, full of divine virtues. Changing base metals into noble ones became possible by adding these active principles, shifting their core nature. This wasn't about magic, but extending natural inquiry beyond simple mechanics. Alchemy delved into divine interactions with matter, enriching mathematical physics. Newton's work decoding biblical prophecy also slotted into this grand plan. It was all about unlocking God's roadmap for history. Daniel and Revelation laid down hints about when true religion got twisted and how it would get back on track. Cracking these prophecies allowed a better understanding of humanity's spot in God's plan. Newton reckoned he was living during a long stretch of decline foretold before a big reform came. He was spot on with his work on timelines, showing how old wisdoms evolved and blended. His interest wasn't just about digging into the past. Newton wanted to grasp how knowledge moved through time. By tracking how Egyptians, Greeks, and Hebrews shared and tweaked original revelations, he figured out which traditions kept the faith intact. History revealed the decay Newton aimed to mend with his restoration effort. At the heart of all his projects was keen observation and careful text analysis. Whether he was studying light through prisms, flipping through ancient texts, or doing chemical experiments, Newton was all about detailed empirical methods. He looked at evidence critically, compared sources meticulously, and made cautious conclusions. This approach steered both his science and biblical studies. Newton used the same methods in physics for his theology work, treating scriptures like scientific data. He compared different versions of texts, found discrepancies and additions, much like a scientist sorting through specimens. Through this, he identified corruptions and separated true revelations from human tweaks. This method rattled those who believed scriptures were entirely divine. Similarly, in alchemy, he didn't just swallow old ideas, he tested them. Through thorough experiments, he noted results and adjusted based on his observations. This experimental mindset linked his work across fields others viewed as separate. For Newton, any type of knowledge required proof, no matter the field. Math was another key aspect of Newton's broad interests, even if not as noticeable as his experimental methods. He openly used math to explain motion and gravity, but it also played a part in figuring out historical dates with stars. Even prophecy interpretations involved calculations. Newton saw math as reflecting God's rational design of the universe. The harmony in planet movements showed God's perfect order and beauty. Ancient thinkers noticed this too, which explains Pythagoras' focus on math. Math provided a window into divine wisdom, underpinning everything. Newton's wide approach explained his remarkable drive and achievements across fields. He wasn't just trying out different hobbies, but was deeply focused on uncovering divine wisdom. This was crucial to him, way beyond simple curiosity. It also explains why he kept a lot of his work private. Controversial theology could derail his mission. Publishing half-baked alchemy ideas might expose sacred knowledge to ridicule. So, Newton held back what wasn't ready, while sharing what could aid broader understanding. Unfortunately, this complete vision faded after Newton's era. Those handling his documents kept his theological and alchemical writings under wraps to preserve his image. The Enlightenment cast Newton as a rationalist, leaving out the theology that truly drove him. The neat image of Newton didn't match the real man. Modern scholars have pieced together his unified vision from his papers. We now see that for Newton, physics, theology, and alchemy were all connected. This shifts how we understand his known works, uncovering deeper meanings. The theology in his general scholium isn't just small mentions, but core beliefs that powered the whole Principia. It's hard to fully understand Newton's perspective because his world and ours are so different. Nowadays, we tend to keep science and religion in separate boxes, and we draw a clearer line between hands-on experiments and deep philosophical thinking than Newton did. We like to section off different areas of study, which hides the connections that seemed obvious to him. His combined approach had its share of challenges and contradictions that were tough to completely sort out. The whole idea of how God's actions meshed with the natural world wasn't easy to pin down. Was matter self-active, or did it rely entirely on God's intentions? The relationship between math and physical reality was another ongoing head-scratcher. These tricky problems sparked lively debates, urging future thinkers to tackle fundamental questions about how we explain things scientifically. Is physics just there to outline how things happen, or should it also explain why they happen? Can we separate scientific investigation from deeper beliefs about what reality is made of? Newton's work pushed these questions to the forefront, sparking philosophical conversations. His influence goes beyond just the realm of science. It shapes how we think about exploration and discovery. The field of mathematical physics he initiated set the standard for all precise sciences, yet the philosophical challenges his work highlighted still drive discussions on how we conduct science and think about what's real today. We're still wrestling with some of the puzzles Newton pointed out, even if we've moved beyond his direct answers. Seeing the full picture of Newton, his public achievements in science paired with his private explorations in theology and alchemy, reveals an incredibly varied and deep mind. He excelled in mathematics, physics, astronomy, optics, theology, history, chronology, and chemistry, seeing connections across areas where others saw boundaries. This holistic view fueled all his achievements. Newton's all-encompassing approach challenges our ideas about how brilliant minds work and what drives scientific breakthroughs. We often see science as separate from religious and philosophical beliefs, but Newton's life tells a more intricate story, one where faith and scientific inquiry are intertwined. His unconventional religious beliefs and alchemical work weren't obstacles. They were essential to his wider quest for understanding.